So this is the example of number 7. So we have water 30 centimeter deep is in uniform flow down a 1 degree unfinished concrete slope when a hydraulic jump occurs. If the channel is very wide, okay, estimate the water depth Y2 downstream of the jump. So we have this situation. So and then the surface here is unfinished concrete, 1 degree slope here. We have a hydraulic jump, and you know the energy is will lost after the hydraulic jump here. And the keyword here is the very wide. So I just want to share you what happened if it is a very wide condition like this. So kita tahu if the slope is 1 degree, so we calculate the value of tangent 1 degree, so we get it is equal to 0.01746 and the n is 0.014. So it is from the table, so I will give you in the exam later on. So and then to calculate the height after the hydraulic jump, might be we could use the idea of this equation. Okay, we need to calculate the value of rod number before the hydraulic jump. Okay, so and then this is the equation V1 over square root GY. So we need to get the value of V1 and also Y. So and then to get the V1, we need to calculate using the Y is already given in question. So to get the value of V1 here, so we refer to the Manning equation like this, and we need to solve it. But the problem here is the value of R here is actually the hydraulic radius. So to calculate the hydraulic radius, we need to use the cross-sectional area over the wetted parameter. So the problem is if we don't know what is the width, so might be we cannot calculate the value of hydraulic radius. So, but to simplify this question, so we use this assumption. So if the value of width is too big, it is okay for us to make assumption that hydraulic radius is actually equal to the real depth. So means if the width is too wide, so the hydraulic radius can be taken as 30 centimeters as given in the question. So for this problem, we just use the value of R, which is equal to 0.3 meter here. And then we could get the value of V1, 4.23 meter per second. We could calculate the front number 1 equal to 2.466, and then we could calculate the value of Y2, which is equal to 0.907 meters. And this is the example number 8. So water in horizontal channel accelerates smoothly over a bump. So this is a bump here, and then undergoes a hydraulic jump, and then it will flow like this, and then it has the hydraulic jump at this point. So if Y1 is 1 meter and 1,3 is 40 centimeters, so we need to estimate what is the value of V1, V3, Y4, and the height of H here, and the height of bump. Okay, let's say the same idea. So because point 1 and number 3 is before the hydraulic jump, so we could compare the energy. So so we compare E1 equal to E2 by using the energy. Yeah.
Dia walaupun dalam soalan tak mention apa tu, tak ada energy loss, boleh assume juga.
Okay, saya tunjuk. So memang dalam syllabus kita just assume tidak akan ada energy loss except kalau setelah berlaku hydraulic jump. Okay, kerana kita tak masuk lagi yang, maksudnya kalau dalam fluid 1 tu maknanya ada apa major loss, minor loss dalam aliran kan. So jadi yang itu kita tak masuk. Okay, boleh
Alright.
Okay.
Boleh.
So okay, because there are no losses, so we compare the energy E1 equal to E3. So we just use the energy equation. So we get this term. So and then because it is already the value of Y1 and Y3 is already given. So the unknown is actually the V1 and V3. And then as I showed previously, so we could use the continuity equation. Okay, so and then we could have another equation which is V1 equals 0.4 V3. So by using these two equations, okay, you could solve the problems, then you could get the V3 is equal 3.740 meter per second and V1 is 1.496 meter per second. So that is for question A and B. So we could get the velocity for 1 and 3. So and then we need to calculate the height after the jump. And we could calculate this one by using this equation. So this new equation is already introduced to you in previous slide. So you could calculate all of them, and then you could get Y4 is equal 0.89 meters. So, and then this is the new idea. I would like to introduce to you what happened, what kind of calculation that we could use or we need to modify in our equation if we have a bump. Okay. So first, first we compare energy at point 1 and point 2. So let's say we have point 1, point 2, and point 3 here. These 3 points is located before the hydraulic jump. So then we could compare, we could equalize energy at point 1 is equal to energy at point 2 and energy at point 3. However, for point number 3 and point number 1 here, we measure the height of water is from this datum until it surface. And we call this height is Y. And then for point number 2 here, the actual term for Y is from the bottom of the open channel to the free surface. So means that the Y here is from here to here only. Okay, that's why we need to add another parameter, which is the value of H, the height of this bump, because to make sure that our calculation will be based on the same level. Okay, so that the first idea, and the second one is the increment of height of bump here will give another will create an extra potential energy. You could imagine that if water flow like this and then they climb into a bump like this, so it will create another higher velocity at this point because you give it potential energy. Okay, that's why when we compare point number 1 and point number 2, at point number 1, we just use this equation of energy equation. And at point number 2, we still use the same energy equation, but we add a parameter of H here to reflect the height of bump that create level to increase the potential energy. So, and then we substitute everything, all the value that we have. In equation number 3 here, we have 3 unknown parameters, so which is Y2, V2, and H. So, and then another assumption that used for open channel is the previous question we use front number 1 when it's flow on the surface, and at the same time, okay, we assume that the flow bumps will always have the critical flow, and we could assume that on flow bump it is equal to front number 1. Okay, so we have the surface and then we have the bump, so we could assume that the front number is equal to 1. So because we already know the float number is equal to 1, so we could calculate by using the float number here. So we could substitute all the value. So and then we could have equation number 4, which is V2 square is equal 9.81y. And then we compare equation number 3 and number 4. We substitute in this equation, so we could reduce from three unknown parameter to two unknown parameters. So we substitute the value of V2 here. So now we get equation number 5, which is only the value of y and h. Next, we are using another equation which is come from the continuity equation. So we could we just use y1 v1, so we could eliminate the effect of width because it is constant, so we could eliminate from left hand side and right hand side. So we substitute the value, we could get equation number 6 here. So I think you already know what to do. We could solve this equation simultaneously. So finally, we could get the value of y is equal 0.61 and V2 here is equal 2.456 meter per second. So and then after we know everything here, so when we know the value of y, so and then we substitute here in the equation number 5, we could get the value of h is equal 0.19907 meters. Okay, we go for example number 9 here. So so we create a situation like this. So we have a 10 centimeters high bomb here. In a wide horizontal channel, water channel creates a hydraulic jump just upstream. So we assume that when the hydraulic jump occur here, and then we have a final flow through the bomb here, and then it's flow like this. So might be a little bit different from the previous question. In this question, we found that there are we have 3 points here after the hydraulic jump. So in this situation, we still use the same idea. Energy at 1 is not equal to energy at 2, 3, and 4 because the hydraulic jump here, so we'll really certain it is equal. There are energy loss in hydraulic jump. So however, the energy at point 2 is equal to energy at point 3 and equal to energy at point 4 because these 3 points is located after the hydraulic jump. Itu yang awak kena faham. So tenaga sebelum hydraulic jump tidak sama dengan tenaga selepas hydraulic jump, tetapi apa sahaja tenaga, apa sahaja location selepas atau sebelum hydraulic jump akan memiliki tenaga yang sama. Kerana kita anggap bahawa kita tidak menfikir losses yang berlaku di sepanjang aliran.
So
Yeah.
for point position 3 and 4, so because it already passed through the hydraulic jump, so means that 2, 3, 4 will have same energy, but
Yes.
it less than energy at 1. So
Yes.
means that energy loss not include for 3 and 4.
Yes. Okay. So the higher energy is at point number 1, and then when hydraulic jump occur, so you will you have energy loss. So energy for 2, 3, and 4, energy 2 equal to 3 equal to 4, and not equal to 1. But the total energy 1 is the higher one. 1 has greater energy because when hydraulic jump, it lost certain value of energy, then means that the energy at point 2, 3, and 4 is a little bit lower compared to 1. Okay, boleh
Can, but Doctor, can I ask one more question?
Okay.
So how do we know from a problem that how do we know when we will have the hydraulic jump? Because for this question is different than the example at, but the ground is similar. Then how do we determine the hydraulic jump is occur at which point?
Okay, so actually in our syllabus, we are not going to determine when the hydraulic jump will occur. Okay, so but the common idea is we check its Froude number. If the Froude number is greater than 1, so means that the hydraulic jump must occur. Okay. Okay, but in our syllabus, there will be no question about please determine at what location the hydraulic jump will be occur. No, that's not our syllabus. So we just about the open channel, and then we evaluate the energy, and then we in our question the hydraulic jump will be given. Mean the hydraulic jump, the location of hydraulic jump will be given in the question.
Okay, thank you, Doctor.
Okay, thank you. Okay, that's our syllabus. If not, I need to add more more notes about determining the hydraulic jump in open channel flow. Okay, boleh?
Boleh, Doktor.
Okay, so we continue to answer this one. So this is the question. Okay, so the question is we need to estimate what is the value of V4 and Y4 here, and then we need to calculate what is the V1 and then what is the Y1. Okay, so for V4 and Y4, so we assume, so this is another assumption, so it is actually the same. So when we have bump, we could assume that the Froude number is equal to 1. So and then so we could have at V3 here, we could calculate the velocity at point 3 at the bump is equal to 1.72 meter per second. So and then the flow rate at 1, okay, because it is the width here is constant, so we could calculate the continuity equation by having y1 a1 equal y2 a2. So at this case, in this case, we use point number 3. Okay. So again, I would like to remind you, the energy before and after hydraulic jump is not the same because the hydraulic jump is a losses. Okay. Okay. But the flow rate before and after hydraulic jump must be the same because we are dealing with incompressible flow, which is water. So to maintain that the flow is according to a certain ratio, okay, means that we could compare the point before and after hydraulic jump. Okay, yang itu saya harap awak dapat faham. Kerana kita menggunakan air dan air adalah incompressible fluid. So and then we could calculate the flow rate here. So for flow rate at point number 3, so which is V3Y3, so we could calculate it is equal 0.516 meter cube per second. So and then we could compare the energy at point number 3 and number 4. So because it is both after the hydraulic jump, so it has same amount of energy. However, for point number 3 here, okay, for point number 3 here, we need to add a value of H because we have bump at that point. And then we substitute all the value here. So we substitute the value here, so we could create equation number 1, which is the value of Y4 and V4 is still unknown. And then to get this unknown, we just create another equation from the continuity equation. So we could use this one, V3Y3 is equal to 0.516. So we calculated this previously. And then it is also equal to the flow rate at point number 4. So we have 0.516 V4Y4 as equation number 2. Then we could use these two equations to calculate the value of Y4 and V4 as shown here. So and then to calculate the velocity and height before the hydraulic jump. So as you know, that the energy equation right now is cannot be used because we have losses in hydraulic jump. Okay, so we calculate the value for point number 2 because we want to use this equation actually, and this equation need to 2 points, which is one is point before the hydraulic jump and 2 is after the hydraulic jump. So if you see this equation, okay, this equation is actually used to calculating the hydraulic depth before and after the hydraulic jump. That's why we need to calculate the value of point number 2. So this is the calculation that we need to do to get the parameter at point number 2. Because previously, we calculate about point number 3 and number 4. Point number 3 and point number 4 is actually far enough from the hydraulic jump. So we must have point which is just before the hydraulic jump and just after the hydraulic jump. So, however, okay, if you see that this equation previously, we are comparing actually the top value here must be value after the hydraulic jump. Okay, but in this equation, I write it in reverse version because we assume that there are no this idea is actually, this calculation is about to calculate the ratio between y1 and y2. So it means we could use it in reverse direction. So mean if you want to use the reverse direction, okay, previously point 1 is the before hydraulic jump. Previously we write value at the top here is the after hydraulic jump, and value at the bottom here and the float number is the value before the hydraulic jump. Okay, but you could also use this equation for the reverse condition. For example, the value at the top here is the value of before the hydraulic jump. Then you need to substitute the value of point at the bottom here and the value of the float number here for the value of after the hydraulic jump. So that what I use here. Okay, so I use the same equation, but the location of point number 1 and point 2 mean the location of before hydraulic jump and after hydraulic jump is reversed now. So we could and then I could calculate the float number for point after the hydraulic jump as 0.472, and then we could I substitute in equation number 3, and then I could get the value of y1 is equal to 0.165 meters. And then from the continuity equation, as I said, because we are dealing with incompressible, so we could calculate the continuity equation whether it is whether it has hydraulic jump or not. So the continuity equation is remain conserved. So we could calculate the value of V1 equal 3.12 meter per second. Yes, saya.
Boleh tak doktor explain sekali lagi yang kenapa doktor inverse untuk before and after punya hydraulic jump?
Okey. Yang paling mudah sekali idea ni ialah saya rasa dalam fleet 2 kita belajar Mach number, betul kan?
Betul.
Ada. Mach number tu sebenarnya adalah ratio. Kalau awak nampak kita ada P2 over P1, betul kan? Ada rumus apa nama tu, ada ada gamma 1/2 gamma kuasa berapa, ada kan? Okey, kalau awak ingat sewaktu kita belajar Mach number tu, kita boleh aja guna dia terbalik, betul kan? Maknanya okey, boleh nampak?
Boleh.
So maknanya mana depan mana belakang tu kita boleh reversible. Sebab kita anggap dia adalah satu pengiraan berdasarkan maknanya ratio ketinggian air before dan after after hydraulic jump. Maksudnya kalau normally orang akan kira selalunya before data before hydraulic jump ni lebih banyak. Okay, normally sebab selalunya hydraulic jam ni dia akan melalui certain something baru berlaku hydraulic jam.
Okay.
Okay. Maksudnya dia just comparekan ratio sahaja sebenarnya. Maknanya kalau awak buat derivation ni, pembuktian equation ni dia hanya ratio. Oleh itu, kalau katakan kita nak buat ratio after hydraulic jam over before hydraulic jam, dia jadi katakan 1/2. Tapi kalau awak terbalikkan pun, everything awak akan terbalikkan kan? Bawah naik atas, atas turun bawah, betul kan?
Betul Doktor.
So jadi ratio dia tetap sama, betul kan?
Oh, okay.
Itu aja sebenarnya idea dia. The main concept is ratio.
Ratio je lah.
Ratio aja. Jadi maknanya kalau awak nak cakap A nisbah B 1 nisbah 5, orang cakap B nisbah A 5 nisbah 1, still sama, betul kan?
Betul Doktor.
Okay, itu aja sebenarnya.
Okay. Faham.
Okay, so.
Thank you Doktor.
Doktor, kalau nak buat ratio Y2 per Y1 tu, nanti fraud number tu akan tukar kepada 1 kan?
Ya 1. Yang itu je awak kena jaga.
Lepas tu 2
Tapi
tu
yang-
nanti jadi 1/2.
2 tu memang dekat atas lah Doktor.
2 tu kat atas.
2 ke atas.
Bukan, jangan awak tukar 2 ni turun bawah pula. Jadi kalau awak katakan nak tukar ini, nak tukar jadi 2Y2, sini Y1, fraud number kena Y1. Fraud number ni kena ikut yang bawah ni. Okey, boleh?
Okay, boleh Doktor.
Okey. Okey, yang ini semua saya rasa awak boleh nampak pengiraan, dan kita masuk soalan yang terakhir. Ini soalan yang terakhir tapi agak panjang kerana soalan terakhir ini kita kata dia melibatkan keseluruhan perjalanan. So maknanya, for in example 10, we have a horizontal flow of water through a sluice gate. So, and then a hydraulic jam ada berlaku. So, and then we have a crested wear. So, yang ni saya rasa pun ada nota berkaitan dengan crested wear. And then the jam, unfinished concrete whatever here, and then we need to calculate the flow rate, the normal depth, the Y here, Y2, Y3 and Y4. Okay. So yang ini ceritanya ialah apa? It is about when we have a dam here, so and water from dam release. So because the energy is higher, is high, so it will create it has very high possibility to create a hydraulic jam. So what engineers should do, we need to do something to stop the energy, the hydraulic jam, at least to neutralize the flow. So what normally engineers do, they will put a barrier here. So and then the water will flow like this, and then they will create a normalized flow at the end. Okay, so this is the whole story about the existing hydraulic jam. Okay, and then kita ada melibatkan wear kat sini. Yang ini ada melibatkan pengiraan yang ada dalam nota yang saya tambah tu. Okay. Okay, so we are calculating this one with a very dengan teach bit all the coefficient. Okay, first we want to calculate the flow rate. So the flow rates mean the velocity or the flow rate when the water start flow through the sluice gate here. Karena this is a dam, so we assume that water at dam is normally static. Okay, awak pun akan ambil nilai velocity pada permukaan equal to 0 if you do the velocity, if you use the Bernoulli equation. Okay, so and then the water gate here, so and then it's depend on, so you may use you may refer my notes. I already upload new notes in my website, so please refer to that notes, because in that notes dia ada banyak rumus yang berkenaan dengan water gate semua sekali. So this is actually the fixed notes from the textbook. It's depend on the situation. Okay, so let's say yang ini yang kita belajar sebelumnya, this equation is already appear in fluid mechanics 1 when we learn about Bernoulli equation and flow rates. Okay, so kita ada pembuktian sekali waktu dalam fluid 1. Okay, so the idea is to calculate the flow rate at water gate like this is discharge coefficient CD, H mean the height of the slice gate, and B is the width of the slice gate, and then the square root 2G and Y1. So Y1 is actually 2GH. In fluid mechanics 1, we learn as 2GH, but in this syllabus, we will use as Y1. So, and then to determine the CD actually, so there is some rules. So for example, we need to determine what is the ratio between H and Y1, because you know, the higher the water level here, they will create a lot of turbulence and so on and so forth. So we need to determine what kind of what region of discharge. So we are comparing H over Y1. So we found that it is equal 1/4, and then it is less than 1/2. So mean that the discharge coefficient need to be calculated by using this equation. Okay, so this please refer to the notes in the website. So and then we substitute all the value here. So we'll find that the discharge coefficient is 0.568, and then we substitute in the equation here, so we get the flow rate at this slice gate is equal to 379 feet cube per second. Okay, so this is just the tricks question. If somebody asks what is the normal depth, so normally in horizontal channel, okay, there are no normal depth. They just use the depth of water. The normal depth is actually occur when we have slope. Okay, because when the water horizontal, if the water is not come from a reservoir like this, okay, the water will not flow. So why the water is flowing? Because the water has a high potential energy because of the difference of water level. So in open channel, for example, in conduit of liquid, so you need to have some slope to make sure that the water will flow. But water flow will create you, okay, for example, I draw here. Okay, for example, we have a water channel macam ini. Okay, kita akan memerlukan slope angle. Okay, normal depth tu ialah kita kata bukan miracle lah, but characteristic of open channel. Walaupun dia berbeza ketinggian, tetapi ketinggian ini kita kata almost constant. Okay, maknanya ketinggian air macam gini lah kalau kita nak ukur. Okay, ketinggian air ni kita kata almost constant. Okay, itu yang dalam keadaan ini kita kata oleh kerana air mengalir disebabkan ada level air yang berbeza, oleh itu by right takrifan dia bukanlah kita kata normal depth. Okay, so kita teruskan kepada soalan yang seterusnya, iaitu Y2. Okay, Y2 kalau kita tengok di sini adalah kita ingin mengira apakah ketinggian air maknanya seketika selepas ia melalui slice gate. Okay, so kita ketahui from the question the width is 8 feet and then the flow rate is constant. Okay, and then we could have equation like this. The flow rate is 379 and it's equal to A1 V1. So we substitute all the value. We know the height, we know the width. So and then we could calculate the velocity at point number 1, which is 3.95 feet per second. So and then we could calculate the energy at point number 1 by using the energy equation. We substitute all the things, all the parameter here. The gravity is 32.2. So we could get the energy is 12.24 feet. So and then we could compare flow rate for point number 1 and for point number 2. So we found that we don't know the value of Y2 and V2. So it is okay. So we name this equation as equation number 1. Then we could equalize, we could do the simultaneous solution. with the energy equation here. So the total energy at point number two is equal to energy at point number 1, which is 12.24, and then we name this equation as equation number 2. So from equation 1 and equation number 2, we could calculate. So we could get this value. So I simplified this one because I think you already know how to solve this. So and then we have equation, we put in equation number 2. However, the equation might be quite difficult. So we use try and error method. So we get Y2 is equal 1.83 feet and V2 is 25.88 feet per second. So and then in Y3, so we know from the diagram that Y3 it is happen the point 1.3 it is after the hydraulic jump, so we cannot straight comparing with the energy equation. So what we need to do first, we estimate the value of Y by using this equation. So again, so this is the height of in after hydraulic jump, and what number 2 here is before the hydraulic jump. So we know that the Y at point number 2 is 1.83 feet. We could calculate the float number at point number 2 as 3.37 because point 1 and point 2 is already solved. So and then we could estimate the height, the hydraulic depth for point number 3 is equal to 7.85 feet. Then, so we need to estimate, so what is the Y4, point number 4, the height of water at point number 4. So if you see the total one is, so we have a flow here, and then a flow will start at the bottom here because we have a bunker here, some plate here, and then water need to climb this wall. So and then we need to calculate what is the height of water from the step here, from the top of the plate here to the free surface of the water. And then we need to determine what kind of wear. So the idea is because we have thin plate wear, so you please refer to the extra notes that I given in the website about thin plate wear. So the flow rate for the thin plate wear is CD, discharge, times B is the width and the gravity and the height of the wear. So and then if you see the CD here, so it is the shape is sharp crested wear. So because we assume that the top is a little bit sharp, okay, because the water will not flow. Okay, because the tips here is not so long, so the water is just we assume that it is a quite sharp wear. Okay, and then this CD is actually given in the notes. So okay, and then we substitute the value. So we know that the height is 6 feet and the H is the water from the wear. So so this is the CD. So we use this CD in the next equation. So we know that the flow rate is constant. So the flow rate is 379, and then this is equal the flow rate for the wear. So I mean this flow rate is the flow rate that we get here. Okay, means this flow rate is actually, if you see the diagram here, is the flow rate about this one. We do not take flow rate that we calculated previously for the slice gate here. So we need to calculate separately about here. Okay, so we substitute the value of CD, and then we substitute all the parameters here. We found that the H, we have one equation like this, and the only unknown parameter is the H. So, and then we could use try and error method. So we could calculate the the value which is h is equal to 5.53 feet, and then again we substitute the value at the CD, because in CD we left some equation in CD. Okay, we have for y. Okay, and then we could get the CD here is 0.642, and then the y is the total, means the height of water above the weir and the height of its weir, which is 6. So and then it is 11.53 feet.